In this section, I'm going to talk about present value annuities. And so basically, you'll see that I just copied the same intro here that I have for future value annuities that just sort of explains the difference between the two types of annuities. So if you need to revisit this, you can. But basically, let me explain to you what a present value annuity is to help you understand that, and then I'm going to develop the formula. So let me first attempt with this simple little diagram here. In the previous section, we talked about future value annuities, and basically in that situation you start at, say, time 0, and then you make your first payment, you make your second payment, you make your third payment, and so forth. Well, then at the end of your entire time period, in other words, after you've made all those payments, then each one of these payments add up to a future value, but not only do the payments add up, but also the interest that each payment earns adds up to a future value. Now, for a present value annuity, it works different. A present value annuity is like you have a present value now. In other words, your money might be worth now, say you might have $10,000 today, and then you want to know how much you can withdraw each period from that present value so that you can, at the end of taking out your last payment, you have nothing left. So this actually works a couple of different ways. One way is, suppose you put suppose I put some money in a bank for you as a trust fund of $10,000, and then you take out so much money a month, say over a couple of years, and then we could figure out what payment you could take out per month that would be equivalent to $10,000. Now, in that situation, the actual payments would actually add up to more than $10,000 because this present value that I put in the bank initially earns interest. And so every time you take a payment out, what's left in there earns interest. And another way to think of this is maybe you borrow $10,000 from a bank, so you owe the bank this $10,000, and then you make monthly payments on that $10,000 until you pay that off. And again, what you owe on what you're left in the balance, in other words, what you're left owing after you make each payment, is charging you interest each month. So you're actually going to make payments of more than $10,000 over the time period that it takes to pay it off. So anyway, let's go ahead and look at an example here. Suppose you want to make quarterly withdrawals from an account that earns an annual interest rate of 6% for a period of 2 years. How much must be initially placed in the account in order to make these withdrawals? Okay, so now let's think about this for just a minute. You're going to make quarterly withdrawals here. So we have quarterly withdrawals. So that's 4 times a year for a period of 2 years. So that's 8 withdrawals. So you know you're going to withdraw $16,000. Now, but here's the catch. You don't need $16,000 in the account initially in order to be able to do that. Because if you were to put $16,000 in the bank at this point right here, and you take these $2,000 each period, then you're not going to have a zero balance at the end. You're actually going to have a little bit of money left over here because your $16,000 will earn interest. So actually the amount you're going to need is going to be less than $16,000 because the money's going to earn interest. So what we're going to do is we're going to find out a formula. We're going to find a formula that will show you how much you need to have in the bank so that you can withdraw the $2,000. Okay, so again, let's review some facts. We know the quarterly payment is $2,000. The annual rate is 6% or 0.06. The compounding schedule is quarterly, so M is 4. The number of years is 2. So since we know the rate is 6% compounded quarterly, we know the quarterly rate would be 0.015 or 1.5%, and we know that N would be 8 total periods. Now, if you go back to this compound interest formula, now notice this is the compound interest formula for finding P if you know the amount. And so basically what we plan to do is we plan to make 8 withdrawals of $2,000. So you can think of this up here as this is a $2,000 withdrawal, this is a $2,000 withdrawal, this is a $2,000 withdrawal, and things like that. But here's the question. How much would you need to have in the bank today to withdraw this $2,000? And then how much would you need to have in the bank today to withdraw this $2,000? And how much would you need to have in the bank today to draw this $2,000, and so forth? Well, if you find out how much you need in the bank for each of these 8 withdrawals today and add that up, then that's actually the present value of your annuity. So the way to figure that out is just calculate the amount of principal that you need to withdraw a $2,000 amount, okay? And then the only thing that will change, I will stay as it is up here, 0.015, but the only thing that would change each time would be the number of compounding periods. Because if you go back and look up here, let me show you. This first withdrawal, if you want to take out this first withdrawal, then how much would you have to take out this payment? Well, the money's only going to go through 1 compounding period. And then for this payment, the money's going to go through 2 compounding periods. For the 8th payment, the money's going to go through 8 compounding periods, and so forth. Okay? So let's look at it. Let's start at the 8th withdrawal, the very last withdrawal. The 8th withdrawal earns 8 periods of interest. So the amount of principal you would need for that withdrawal would be 2,000 times 1.015 to the negative 8, which is this number. The 7th withdrawal would go through 7 periods of interest, so you would need 2,000 times 1.015 to the negative 7, which is 1802.05. And notice it's increasing each time, because as you get closer and closer to where you started, then you're going to have more money because the compounding periods are going to be shorter. 6th withdrawal will go through 6 periods, so you'll need that much. The 5th withdrawal will go through 5 periods, so you'll need that much. The 4th withdrawal goes through 4 periods. The 3rd withdrawal goes through 3 periods. The 2nd withdrawal goes through 2 periods. And then the 1st withdrawal only earns 1 period of interest. So basically what we're saying here is in order to have $2,000 to make your first withdrawal, you'd have to have 1970.44. In order to be able to take $2,000 out after 2 months, you'd have to put in 1941.32. In order to have $2,000 after 3, I said months, it's actually quarters. To be able to withdraw $2,000 at the end of 3 quarters, you actually have to have 1912.63. And after 4 quarters, you'd need 1884.37, and so forth. But you got to have all this in the bank initially. So if you add all of these up, that will tell you the total investment that you would need to invest. So you would need to have $14,971.83. Okay, so now again, this is a long way to do the calculation. So let's see if we can, let's simplify this calculation. So you saw up there what I did was to get the present value, I said I needed to take the 2,000 times the 1.015 to the negative 1 and the 2,000 times the 1.015 to the negative 2 all the way up to the 2,000 times the 1.015 to the negative 8 and add all those up, and that tells me the present value that I need to have initially in order to make those 8 withdrawals. Now let's multiply each term above by 1 plus I, so 1.015. So if we multiply this by 1.015, we just get present value times 1.015. If I multiply this by 1.015, I'm just going to get 2,000. If I multiply this by 1.015, I'm going to get 2,000 times 1.015 to the negative 1. And so every time I multiply these by 1.015, the exponents are going to increase by 1 unit. And so when I multiply the last one by 1.015, it's going to increase this exponent from negative 8 to negative 7. Now, let's subtract the top equation, this one, from the bottom equation. So here's the bottom equation, and here's the top equation. And if I take this equation minus this equation, on the left, I'll get 1.015 times present value minus present value. Well, if you take 1.015 minus present value, that'll just give you 0.015 times present value. And on the right-hand side, if you subtract each of these terms, basically you'll see that these terms will cancel. So every term would cancel except for 2. In the top, you would have the 2,000, and in the bottom, you'd have the 2,000 times 1.015 to the negative 8. So on the right-hand side, as I just said, you'd have 2,000 minus 2,000 times 1.015 to the negative 8. And then if you factor the 2,000 out of those, you get 2,000 times 1 minus 1.015 to the negative 8. So, putting these together, on the left-hand side, you got 0.015 times present value. On the right-hand side, you have 2,000 times 1 minus 1.015 to the negative 8. And then to solve for present value, just divide both sides by 0.015. And now you get a formula. And if you plug this in, if you calculate this formula, you'll basically get the same answer I got up there by when I did it the long way. Now, this formula is really just, if you think about it, the 2,000 is just the payment. So that's just payment. The 0.015 is just I. And 8 is N. So if you think about this, this is just payment times 1 minus 1 plus I to the negative N, all divided by I. And that's actually exactly the formula that we get for the present value of an ordinary annuity. So to calculate the present value of an ordinary annuity, its present value is equal to the payment times 1 minus the quantity 1 plus I to the negative N, all divided by I. And you already know that PV is present value, PMT is payment, and you know I is the rate per period, and N is the total number of compounding periods. So if you needed to know what present value you needed to put in the bank today to withdraw a certain amount of payments given a certain compounding period and over a time period, you could use this formula. Now, if you knew the present value and you wanted to calculate the payment, so in other words, let's say I knew how much money I had in the bank, let's say I knew that I had a certain present value in the bank, I don't know, maybe $10,000 or $20,000, and I wanted to know what payment I could take out each period so that at the end of the time period, when I take out the last payment, there's nothing left, I could use this formula. Now, this same formula is also used for calculating the payment on a loan, and we'll see that in the next video on how we use this formula to find the payment for a loan. So that completes the development of the formula. So for the present value of the annuity formulas, you have two formulas. One formula for calculating the present value and one formula for calculating the payment. And that formula is called the amortization formula. And so we'll work some problems on this in the next video.